Okay, so we're almost there. Almost done with this rotational stuff. We've covered rotational kinematics, we've covered rotational dynamics, we've covered rotational energy. Can you guess what we're going to talk about today? Okay, this basketball, when it spins, has what we call rotational inertia. It's spinning around and it will continue to spin unless something stops it. In this case, it's the friction between my fingers or air resistance or whatever it is that actually stops the basketball from moving. So this rotational inertia, if you go back to Newton, when he was talking about Newton's first law, objects in motion remain in motion, the same applies for things that are spinning as well. Okay? Now, if that's the case, remember, Newton also talked about momentum. So when this thing's spinning, it has a momentum. It has an angular momentum. On your worksheet, go ahead and fill out that first part of this where it takes you through all the different equations that we had linearly and see what they are when we have them in terms of rotational stuff. This is a good review of all those different equations. You're going to get down to the one for momentum. What is the variable that we use for momentum? Normal momentum is given the variable p. And if you remember, it was p is equal to m times v, mass times velocity. And if you filled out that table, you probably got to the bottom where you saw there was a capital L. A capital L is what we use for angular momentum or rotational momentum. And that's going to equal, instead of mv, we need a variable for m, moment of inertia, I, times angular velocity, omega. So our equation for angular momentum is L is equal to I times omega. Now if you remember, the most important thing with momentum and energy is this idea of the conservation of momentum and the conservation of energy. So momentum has to be conserved. I want to show you an example of how this works. I have this turntable here. And if I stand on this turntable, I'm going to hold these bricks just for fun. I can actually spin. You can see me spinning on this turntable. I have angular momentum. And my angular momentum depends upon two things. It depends upon my moment of inertia and how fast I'm moving, my angular velocity. Angular momentum must be conserved. So if I change my moment of inertia, what happened? I speed up, and then I slow down, and then I speed up, and then I slow down. Let me show you that a little bit quicker. See if I can't spin. So this is my angular momentum is right here. And if I pull these in, pull them out, pull them in, ooh, pull them out, you can see that my angular velocity changes. Hold on a sec. Okay, so I got dizzy. Now, why did I get dizzy? I got dizzy because I was spinning around. And when I stopped, the angular momentum of the fluid in my ear continues to spin a little bit. And that's actually what makes you dizzy, is the fluids inside your ear that are continuing to spin. You can actually try this at home. Next time you come to school, we can play with this thing. But try this at home. If you stand up and just put your arms out like this, pull your arms in, and you will feel yourself get faster. Go ahead and try it for a second. This is a huge deal in sports. In sports, we always say that you want to stay low, and you want to keep your center of mass on between both feet. But if you think about it, like hockey, for example, I had somebody in hockey tell me that when you go up, if you want to turn in hockey, you pull the stick into your chest and you make that turn, then you pull the stick back out. That allows you to spin a lot quicker. You see this in football. They're going to go and then they stand up and they spin real quick. You see this in diving. This is huge in diving and gymnastics. If you want to pull out of a spin, you widen yourself out, and that slows down. That's the whole point behind diving, is you tuck yourself into a ball to make yourself go faster, and then at the right time you pull yourself out so that you hit the water or the mat or whatever it is you're hitting at the right angle that you want to hit it at. This is in all sports. Okay? Baseball is a good example. When you're a pitcher in baseball, okay, one of the things they do, or when you throw a baseball, you start out. You see a lot of pitchers put their hand out here. They put their hand out here, the ball's back here, and then when they pitch, they pull their hand in. They start wide and they pull their hand in. What that does is that decreases their moment of inertia, which allows their body to spin faster. Quarterbacks do it too. They're like this and then they throw. They pull that glove in or they pull the hand in. That turns their body quicker and you can get more velocity on the ball. The classic example of this, of course, is figure skating. Figure skaters start that spin really wide, and then they really tuck in, and they go faster and faster and faster and faster and faster, and then they come out of it. That was very graceful. They come out of it whenever they're ready. So this idea of angular momentum is huge in sports. We see it everywhere. We see it when stars collapse. If you get a star that starts to collapse, it starts to spin faster and faster and faster. This is actually why our sun actually has a rotation. This is why our Earth has a rotation. It's because as the Earth started to condense, even if it was spinning a little bit, as it gets more dense and more dense, it starts to spin faster as more things hit it. So all of this stuff has to do with angular momentum. It has to be conserved. If you decrease the radius, you're decreasing the moment of inertia, which increases the angular velocity. On your worksheet, you've got several problems to work through to kind of give you some more reinforcement on this concept. If you have any questions on those, please come and see me, and I'll see you next time.
Thank you so much for watching. If you like science and you like this video, feel free to like this video below and subscribe for future updates.